Hello, today we're going to look at distance time graphs and linked to that, looking at an equation that you'll need to use, probably quite familiar actually, looking at different gradients of the line, so different steepnesses of the line and what they mean, and then we'll look at describing distance time graphs and then how to do calculations from the graph. Only continue with the video once you have a bit of paper, a pen, a pencil, a ruler, a rubber. You'll also need a calculator, ideally a scientific calculator, but if you only have your phone calculator, that will have to do, but ideally a scientific one. And as ever, of course, you need to have your brain switched on. So the first thing to do is to think about what you already know, so on the distance time graph topic. I've done the first one to get you started. So I've called them headlines, but they could equally be called titles or topics. So the first one I just thought of, well, I already know that distance is measured in meters. So now over to you to think about 5 or 6 other ideas that you already can remember on this topic before you carry on with the video. So hopefully you've given that a go, and let's look at some of the ones that I've come up with. So I've also remembered that time is measured in seconds. Maybe in maths or maybe in science lessons as well, we know speed equals distance divided by time. The gradient of the line, well, the steeper the line, that tells us the faster the speed of the object or the velocity. And if it's a flat line, so a horizontal line, then that means the object is not moving, and a posh name for that is stationary. And the unit for speed is meters per second. But you may have got your own, or it's very similar to the ones that I've had. So sometimes it's important to think about why I care about a topic. Well, here are 3 reasons that I've come up with why speed or distance time graphs may be considered important. So the first one is Jessie Combs, and she has just set a world record. So let's just see what she's done. So this article is from the 25th of June 2020, and it's one about Jessie Combs, who's just been given the female speed record for when she sadly at the same time passed away in trying to achieve the record in 2019. So you've got the link, but it's something that you may be interested to read through, as it's just been released this week. And if you do choose to read it, as you will see, she managed to get up to 522.783 miles per hour, beating the previous record from 1976, which was 512.7 miles per hour. So a massive achievement. A question that I often get asked in the car is, are we nearly there yet? Well, that's another reason to know about speed, because if you know about speed, you can calculate how far you've got left to go, or the time that it's going to take you to get there. And another thing that might interest you as well is the speed of light, and equally the speed of sound. So the speed of light is 300 million meters per second. So light travels 300 million meters every single second. And then the speed of sound is 330 meters per second, and that will help explain why when you have thunder and lightning, the thunder, the noise, comes a lot later than the lightning, because the sound travels far, far, far slower than the bolt of lightning. Another use for speed, distance and time are GATSO or speed cameras. So what they do is they measure how far the car is moving. So along the road will be a series of lines, and the camera will know when the car started and when the car ended. It knows the distance between those 2 points. If it knows the distance and knows the time, it can calculate the speed. So if we quickly familiarise ourselves with the equation, so speed equals distance divided by time. Distance, the units are generally given in meters, time generally in seconds, and then speed are given the units meters/seconds or meters per second. Some people like the idea of triangles. So we've got distance divided by time, and that then leaves velocity to go in the gap. And then from that, by covering up the one we want to find, so let's say time, cover up time, that then gives distance divided by velocity, or if we want distance, that gives us velocity times time. And I've just written them out here just so you can see them. So the skill with this topic is to start to read and understand the information, apply the knowledge on graphs. So on the y-axis I've got distance, and on the x-axis I've got time, and I've also got an orange line. So what does that orange line tell us? I personally prefer just to think about it in terms of numbers, so let's just put some random numbers up the distance line and also across on the timeline. So hopefully this makes it a little bit easier to understand what's going on. So we've got an object and it's moving, and at some time later it's moved 6 meters away, and it's taken 15 seconds to get there. Let's remind ourselves of the equation. Speed equals distance divided by time. So if we're saying that the distance is 6, and we're saying the time is 15, we can then get our calculator and work out the speed by doing 6 divided by 15, which equals 0.4 meters per second. So at all points on that graph, the object is travelling at 0.4 meters per second. In other words, it's moving at a constant speed. And that just means it's moving at the same speed. So every single second, it's moving 0.4 meters. So I've now added an extra horizontal line, but let's just remind ourselves that the first part from the previous slide was constant speed. But what does the next horizontal line tell us? Well, let's just look at what the distance is, and at all points the distance is 6 meters. So at the start at 15 seconds and at the end at 25 seconds, the object was the same distance away. Both of them are 6 meters. In other words, the object has not moved. It is stationary. So far the object has started with a constant speed of 0.4 meters per second, then after 15 seconds, for 10 further seconds, has remained stationary. So again, let's just remind ourselves of what we know so far. So the object started at a constant speed, and then for some time, 10 seconds was stationary. But now what has happened? Just so that we can focus on that one last segment, I'm just going to delete the writing on the page. I'm just going to draw a series of lines just so I'm clear with what I need to calculate in order to then calculate the speed of the object at that particular point. So first of all, I need to see that it starts at 6 and ends at 10, and also it starts at 25 and ends at 40. So if we just do 10 minus 6, and that gives us 4, and then if we do 40 minus 25, that gives us 15. So back to the equation. So speed equals distance divided by time. So we know that it has travelled 4 meters, and we know the time taken is 15 seconds. And then 4 divided by 15 in a calculator gives you 0.27, and then the units would be meters per second. So we now know that the object started at 0.4 meters per second for 15 seconds. For a further 10 seconds, the object was stationary or moved at 0 meters per second, and for the final 15 seconds, moved at 0.27 meters per second. And what you should also be able to see is that the steepness of the line, or the gradient, is steeper just here, and therefore has a higher velocity or higher speed. The 0.27 has a shallower gradient, therefore it is travelling slower. So it's worthwhile mentioning that each of these segments, or A, B and C, has its own instantaneous speed. So the speed at that instant, at that moment. So 0.4, 0 and 0.27. And then in any journey you would expect the speed to vary as you change direction, speed up, slow down, etc. Sometimes though, you're expected to find the average speed from the graph rather than the instantaneous speed, the speed at that moment. So let's just look now very quickly at how to calculate the average speed. So the average speed equation is average speed equals total distance divided by total time. So the total distance, if we look, is 10. And then the total time, if we look, is 40. And then 10 divided by 40 gives us 0.25 meters per second. So the average speed was 0.25 meters per second, even though at any one moment in time, the object may have been taking a different speed. Another variation of this graph is this one. So you've got constant speed, you've then got stationary, and then rather than it being a straight line, you might see a curve. And what that tells us is the speed is increasing. And if the speed is increasing, that tells us that the object is accelerating. The speed is getting greater, or the velocity is getting greater. So that brings us to the end of the video. And if we can end as we started, so if you can spend some time just thinking of a few new things that you can remember from today. It doesn't have to be 5 or 6, it might just be 1 or 2. But think about what you've learnt from today's video and then try and remember it obviously for when you attempt any questions.